So I'm going to go through and show you how to write the electron configuration and draw the orbital diagram for fluorine. So the first thing that you need to do is I find where fluorine is on the periodic table. So it's a halogen. Okay, and the atomic number of fluorine, just for you to find it, is 9, so really not that bad. And remember, when you're using the periodic table, you're going to read it like a book. So I'm going to start off, and I've got 1s2, because I include hydrogen and helium. Then 2s2, because I'm going to include lithium and beryllium, so 2s2. And then I jump over to the P section, and I've got 2p5. So really not that bad. I've got a total of 9 electrons there, which I should have had. Then for the orbital diagrams, just for you to remember, the s sublevel has only one orbital. And remember, an orbital is just the area, the volume, the shape where you're most likely going to find your electrons. So for S, you've just got this 3D sphere. Unfortunately, I can't draw it in 3D. For P, so there's only one orbital for S. For P, you've got 3 different shapes in that sublevel, and so therefore we say you have 3 different orbitals. So I've got one along the x-axis, if that's my x-axis right here. I've got one along the y-axis, and then I'm going to draw the other one along the z-axis. The z-axis is just like into the computer and out of the computer. So there are 3 different orbitals for P. For D, there are a total of 5. And for F, there are a total of 7. So if you notice the pattern, you've got 1, 3, 5, and 7. So no memorization necessary, just keeping that in mind. So please don't just memorize stuff and then not have any meaning to it. The other cool thing is you really don't have to memorize this, because according to the Pauli exclusion principle, you can only fit 2 electrons in each orbital. So for S, since it only has one orbital, you should only be able to fit 2 electrons. And if you notice the S, that block that we marked off in our notes, it only has 2 different elements for each S area. So like the 2s can only fit lithium and beryllium, that's 2 electrons. For the P, if you count across from boron all the way to neon, that's 6 electrons, because we've got 3 orbitals, 2 in each. If you start at scandium, which is the D subblock, and count all the way across to zinc, which is the end of the D subblock, you've got 10 boxes there, 10 electrons, because there are 5 orbitals, 2 in each equals 10. And then the last, if you look at your lanthanides and your actinides, so the group that's awkwardly right below, if you count those all the way across, you've got 14. Which tells you 7, because 2 in each, that's 7. So don't say, oh, I have to memorize this, because in fact you just need to use the periodic table. Keep in mind where each block is, and that just comes from practice. So what I'm going to do right now is I'm going to draw out the orbital diagram. So for 1s, I only need 1 box. So I drew 1 box. I'm going to write 1s underneath just to make my life easier for reading. Then I'm going to do my 2s, so I'm not going to do electrons quite yet. My 2s, again, S only has 1 orbital, and people had asked what the difference between 1s and 2s is. It's just size. So for 1s, it's a really, really, really small sphere. 2s, it's a tiny bit bigger. For 3s, it would be a little bit bigger, etc., etc. So that's the only difference between your principal energy levels. So this is first principal energy level, this is the second. The only difference is the size it makes the shape. Okay, and then the last one for my 2p, I've got 3 orbitals, so I need 3 boxes. So 1, 2, 3. And now I'm going to fill in electrons. Remember, Pauli exclusion principle tells you 2 in each orbital, and each orbital is represented by a box, and they have to have opposite spins. So for the 1s, I know I have 2 electrons, because that's what the superscript tells me. I have 2 electrons, so I'm going to have 1 arrow up, 1 arrow down. Each arrow represents an electron, so it's an electron spinning upwards in that direction, and then an electron spinning downwards in that direction. Again, for the 2s, because there is a 2 right here, I'm going to have spinning up and spinning down. Now the last rule for you to know is Hund's rule, and what he said was that electrons are going to fill each orbital and they're going to have the same spin, and then, and only then, once they're completely filled, can you go in and have electrons with opposite spins. So what that tells me for this one, I need 5 electrons, so I'm going to add electrons into each orbital and they will have the same spin. So I'm going to do one going up, another going up, and another going up. You could have also done down, down, down. Either way, it's fine. They have the same spin. I've only used 3 electrons. I need to use a total of 5. So I'm going to go back to the beginning now and add 1, so that's 4, and the second one, that's 5. So I'm done. So for this one, it's kind of, oh, and I need to put a 2p. That's kind of self-explanatory. You probably might have written that already. The one where people mess up, there are 2 different things you have to be careful of. So the ones in black, guys, are no-nos. Don't do them. If you do the following, so let's say I have a 2p4, for example, so 4 electrons, not 5. What some people will do is they'll do an electron going that way, an electron going that way, an electron going that way, and an electron going that way. If you do that, you're not following Hund's rule, because he said have them have the same spin, completely fill all the orbitals, and then go back. All right. The other thing people will do, if let's say I have 2p1, they'll say, oh, I only have 1 electron, therefore I only need to draw 1 box and have 1 electron in it. No, since it's p, you need to show that there are still 2 more orbitals that can be filled. They're just not being filled. All right, and that's it.